In this lesson, we are now going to cover applications of exponential functions. In the previous section, we reviewed logarithms and exponential functions, and now we're going to actually get into those applications. This should be review, at least most of it should be review, so this hopefully will be a nice easy section for you. We are going to go into a little bit more depth than we normally do, and I'm going to prove a couple things to you. But other than that, the rest of this should be review. So let's look at the exponential growth model. That's this equation here. We have y is equal to y naught. This y sub 0 is called y naught. And this will represent our initial value. And then we multiply that by e to the power of kt. K is our rate, or what is also known as the growth constant, and T is the time. Now, when K is positive, and it mentions it here, when K is positive, it's going to be growing. If K is negative, it's going to be a decay, and it's going to be decreasing function. Okay, let's look at our first example. We're talking about population growth. We have a population grows according to the function f of t is equal to 200e to the power of 0.02t, where t is measured in minutes. Now, this is important, so I underlined it. We want to make sure that whatever we plug in for t, it's in minutes. Okay, so here's an example of why we have to be careful. This first part of the question says, how many bacteria are present in the population after 55 hours? So this function here tells me what I have after t hours or t minutes or whatever. In this case, we're talking about minutes. Okay, so this is asking about 55 hours, and I can't plug in hours for t because t represents minutes. So I need to make sure that I change this 55 hours into minutes. So I took 55 times 60 to get 300 minutes. Now that is what I'm going to plug in for t. So I plug in 300 for t here and here. When I work that out on my calculator, I get 8,685.7587 bacteria, and I rounded it to the nearest bacteria. Okay, for the second part of this question, it says, when does the population reach 100,000 bacteria? The when tells me I'm looking for my time, which is my t. This is the amount of bacteria we have after a time t that we're looking for. So I'm going to plug in 100,000 for the output and for our y. And then our formula is 200e to the 0.02t. And so I have to solve this for t now. Now from here, I could take the log of both sides and go from there, which is totally fine. But it's much easier if you simplify first before you take the log of both sides. So I'm going to divide by 200 on each side first. Then that gives me 500 is equal to e to the 0.02t. Now I'm going to take the log of both sides. I can take the log of any base that I want. I'm choosing the natural log because I have my base for my exponential function is e, and if I choose that log with the same base, it makes the arithmetic a lot easier. So I'm going to take the natural log of both sides, and that gives me natural log of 500 is equal to 0.02t, because recall, using our log rules, I can bring the exponent down in front, and so that would give me 0.02t times the natural log of e, and we know that the natural log of e is 1. So this is why I picked the natural log of e, because I know that would end up giving me 1, and it would make my arithmetic easier. Now, to solve for t, my last step is to divide both sides by 0.02. And so that's going to give me 310.73 minutes. Now let's look at the financial applications. If you think back to college algebra, we have our compound interest formula, which is the accumulated value is equal to the principal times the quantity 1 plus r over n all raised to the nt. N is the interest rate in decimal format, and n is the number of times it's compounded per year. So, for example, if it's compounded quarterly, n would be 4. If it's compounded semi-annually, n will be 2. So n is the number of times it's compounded a year. And of course, t is in years. Now, we also have this continuously compounded formula. So if something is continuously compounded, that means our n is not going to be some discrete value. So I want to show you where this comes from and how we got it now that we are comfortable with limits. So what we're going to do is we're going to show that as n approaches infinity of our compound interest formula, that's going to approach p times e to the rt, which is our continuously compounding formula, right? Because if n isn't a specific value like 4 or 2 and is continuously compounded, n is going to approach infinity. And we're going to use this very famous limit that as x approaches infinity, 1 plus 1 over x raised to the x is e. And I believe we proved that at the end of Calc 1 in one of our homework exercises. So what we're going to do, we're going to start off to prove this. We're going to take this p out. This is a constant. It's just our principal. So I'm going to pull the p out in front. Then what I'm going to do is I'm going to reorganize this using a little bit of algebra. I'm going to let n be x times r, which also means, if I do a little bit more rearranging, that r over n is the same as 1 over x. So I'm going to replace r over n with 1 over x. And I'm going to replace n with x times r here. Now, because I'm doing some substituting for n, I have to also replace this n here. Now, as if x goes to positive infinity, and r is just some arbitrary constant, it's some kind of a rate like 0.02 or 0.05. If I have infinity here and I have some constant here, the n is going to be going to infinity as well. So I can do a direct substitution and say if n goes to infinity, x is going to go into infinity as well. So as x goes to positive infinity, we have this limit here. We still have our p out in front that we pulled out because that's a constant. And now, using the rules of exponents, I'm going to use the power rule. When you raise a power to a power, you multiply. But I'm going to use it in reverse, and I'm going to split it up. So I'm going to split the x and the r and the t. So I'm going to rewrite 1 plus 1 over x to the xrt as 1 plus 1 over x raised to the x all raised to the rt. So this expression here and this expression here are equivalent based on the power rule for exponents. Now I've got this broken up, so I have the limit as x goes to infinity of that expression that we were looking for. And because I know that this has a limit, I can replace this with the limit, which is e. We knew that from Calc 1. So this is equivalent to e, and then I have p times e all raised to the rt. So this is where we get our continuously compounded formula. So let's go ahead and use this in an example. A 25-year-old student is offered an opportunity to invest some money in a retirement account that pays 5% annual interest compounded continuously. As soon as I see this word compounded continuously, I know I'm going to be using this equation here. Now the question says, how much does the student need to invest today if the student wants $1 million when she retires at age 65? So to go from 25 years to 65 years old, that means the amount of time that has passed or would pass would be 40. So this is going to be my time that I'm going to plug in here for t. That's for this t right here. My interest rate is 5%, so I write that in as my decimal for r, which is 0.05. What I want at the end is the $1 million. So that's going to be my accumulated value. And what we're looking for is P. How much do we currently need to invest in order to have this at the end of the 40 years? So I need to solve this equation for P. So I'm going to divide both sides of the equation by e to the 0.05 times 40. And when I do that, I get $135,335.28. Now, if she could earn 6% annual interest compounded continuously instead, what would she need to put in? So as this interest rate goes up, she would have to put in less because she earns more interest. So if I do the same thing I did here, but I change my 0.05 to 0.06 for that different interest rate, this is the amount that she would have to put in now in order to have at age 65 $1 million. Okay, let's look at the next topic. It's talking about doubling time. It says if a quantity grows exponentially, the doubling time is the amount of time it takes for the quantity to double, and it's given by this formula. So it says the double time would be the natural log of 2 over k, which is really our rate. I keep using r because that's what I'm comfortable with. That's what I've always used growing up. So my r is this k. Okay, so we are going to start with our continuously compounding formula. And I'm going to prove to you that if this amount is doubled, that the time required for it to double is this. Okay, so whatever I put in here for P, if it's doubled, I'm going to replace the accumulated value with 2P. I want to solve for T now. So I'm going to cross off my P's because I can divide both sides by P. That's just some constant amount of money. So I'm going to get 2 is equal to e to the RT. Then when I solve for T by taking the natural log of both sides, I get the natural log of 2 is equal to the natural log of e to the RT. Now, the natural log of e is 1, and remember, I bring this down in front. So I get RT times 1, which is just RT, is equal to the natural log of 2. And then to solve for time, I divide both sides by R. So the doubling time would be the natural log of 2 over R, which is the rate. Now remember, my R here, and my apologies, I'm just used to using R, is the same as this K here. Okay, now let's do an example of using that doubling time formula. Assume a population of fish grows exponentially. A pond is stocked initially with 500 fish. After 6 months, there are 1,000 fish left in the pond. The owner will allow his friends and neighbors to fish on his pond after the fish population reaches 10,000. When will the owner's friends be able to fish? So we've got a lot of information given to us in this problem. And so since we're doing a population growth here, we're going to use our continuously compounding formula. Now, the question wants us to figure out when can this guy fish. So we have to wait till there's 10,000 fish in the pond. So the accumulated value would be 10,000. That's what we want in the future. The initial amount is given to us as 500, so that's our P. We do not know what the rate is, and we're solving for the time, so we still need to know what R is. Now, we can use our doubling time formula to figure out what the R is, and then once we know what R is, we can solve the equation for T. So the double time formula is that you take your double time, and that's equal to the natural log of 2 over your rate. Now, in this question, it doesn't specifically say the double time is, and then fill in the blank, but it does tell us that it starts with 500 and it takes 6 months to get to 1000. That is the doubling time. It goes from 500 to 1000. That's doubled. So 6 months is our doubling time. So remember now, if we set it up where t is in months, that's going to give us this t here in months as well. So 6 months, that's our double time, is equal to the natural log of 2 over r. So r is going to be the natural log of 2 over 6. That's our rate. So I'm going to plug that in here for the rate. Now, I highly suggest when you do these problems, since we're dealing with large numbers and small numbers, I wouldn't round this number and put that in here. I would keep the exact value and wait to round until the end so that those intermediate rounding steps don't mess up your answer. So make sure you wait to round at the very end. Okay, so here we have our equation set up and we need to solve it for t. So I'm going to try to simplify it first by dividing both sides by 500. So I've got 20 is equal to e raised to the power of the natural log of 2 over 6 times t. Now I'm going to take the natural log of both sides. When I do that, I get the natural log of 20 on this side. On this side, my exponent comes down in front because I have the natural log here, and then the natural log of e is just 1. So now to finish solving for t, I'm going to divide both sides by the natural log of 2 over 6. So I have the natural log of 20 all divided by the natural log of 2 divided by 6, and that's going to give me 25.93. Remember, t is in months because that's the double time unit. We have to be consistent. Okay, so that means 20, if we round it to 26 months, it would be a little over 2 years. So the friend would have to wait for more than 2 years to fish in the pond. Okay, let's look at exponential decay models. It's going to be the same as the exponential growth model, except the k is going to be negative because it's decay. It's going to be a decreasing exponential function. Now, one of our applications to a decay problem is Newton's law of cooling. And this is the formula for Newton's law of cooling. This T here is the temperature of the object at time little t. So big T is the final temperature, little t is the time that you plug in, like the time that has passed. T sub 0, that's the initial temperature, and then T sub A is the room temperature. And so this is going to be your constant in front of your E. You're going to raise it to the power of negative RT. That's our formula here for an exponential decay problem, although I'm using R and they use K. And then you add TA, which is the room temperature. So let's walk through an example of Newton's law of cooling. It says, according to experienced baristas, the optimal temperature to serve coffee is between 155 degrees Fahrenheit and 175 degrees Fahrenheit. Suppose the coffee is poured into a temperature of 200 degrees Fahrenheit, and after 2 minutes in a 70 degree Fahrenheit room, it has cooled to 180 degrees. When is the coffee first cool enough to serve? So what we need to do is we need to find time t when the temperature is 175 degrees Fahrenheit, because that's going to be the optimal time to serve the coffee. And that's going to be the first optimal time to drink the coffee, because the optimal time is between 155 and 175. And since it's cooling down, this is when you first reach the temperature that is good to drink the coffee. So we want to find the time it takes to get to 175 degrees Fahrenheit. We know our initial temperatures and our room temperature. What we need to do is we need to find the rate to start off with. So the last part of this question gives us enough information to figure out what our R value is. It says when it's poured at 200 degrees Fahrenheit and it sits for 2 minutes to cool in a 70-degree room, it cools to 180. So all this information we can plug in to solve for R. So this is the final temperature of 180. Looking at Newton's law of cooling, that's this here, the final temperature of the object. This is our initial temperature, so that's at 200. This is the room temperature, so that's 70. The T is 2 minutes. That's how long it waits for it to cool off for 2 minutes. So that's minus 2 times R. That's this here. The R is what we're going to be looking for. And then plus our room temperature, which is plus 70. So I got to use algebra to solve for R here. So I'm going to subtract 70 from both sides. That's going to give me this here. And then I'm going to divide both sides by 130. So that gives me, when I reduce it, 11 over 13. Then I'm going to take the log of both sides. That gives me the natural log of 11 over 13 is equal to, and when I take the natural log of this, the exponent can come down in front, and the natural log of e is just 1. So I'm left with negative 2r. Now, when I solve this for r, I just divide both sides by negative 2. So here's my rate. It's a little messy, but like I said, it's important not to round until the end so that it doesn't throw your answer. So this whole big mess right here is going to go in for r. So now we have our equation for Newton's law of cooling. So we have the 200 minus 70, right? The initial minus the room temperature, that's the 130 here. Here's our final temperature. Here's our rate, and we're going to plug in the time. So this is going to be in minutes, and then we get out the temperature. Although the question is asking us to do it in reverse, it wants to know the time that it takes for it to cool down to 175 degrees Fahrenheit. So I'm going to put this in for T here and solve for little t, so I find the time, not the temperature. So again, to simplify this, I'm going to divide both sides by 130. When I reduce it, I get 21 over 26 over here. And I get e to the negative 0.5 natural log of 11 over 13 times t. Now I'm going to take the natural log of both sides and then divide by what's left over in front of the t. And what we get is 2.56 minutes. So what this is saying is, if we start at 200 degrees Fahrenheit for the coffee and the room is 70 degrees Fahrenheit, when we pour that coffee, it's going to take 2.56 minutes to get down to 175 degrees, which is the optimal time to drink your coffee, between 155 and 175. But this would be the first chance that you would get to drink your coffee. Okay, let's look at the second part of this. When is the coffee too cold to serve? Well, that's when it's less than 155. So we're going to do the same thing, but we're going to put in 155 for our final temperature. I'm going to subtract 70 from both sides. That's going to give me 85 over here. And then I'm going to divide both sides by 130. And that's going to give me 17 over 26 is equal to e to the power of negative 0.5 natural log of 11 over 13 times t. This is where I'm going to take the natural log of both sides. So I have natural log of 17 over 26 is equal to, and then negative 0.5 times natural log of 11 over 13t. So I'm going to divide both sides by this in front of the t. And when we do that, we're going to get 5.09 minutes approximately. So once we pass that 5.09 minutes, then it's going to be too cold to drink. So basically the optimal time to drink the coffee would be between 2.56 minutes and 5.09 minutes after the coffee is poured. So in our last topic of the lesson, we're going to talk about the half-life formula. And the half-life formula, if you notice, looks exactly the same as the double time formula. However, because it's half-life, we're dealing with decay problems, which means our rate is going to be negative. So although they didn't show the negative in this formula, remember the K should be less than 0. So let's look at our example for half-life. It says one of the most common applications of an exponential decay model is carbon dating. Carbon-14 decays at a regular and constant exponential rate, and therefore, if we know how much carbon was originally present in an object, and we know how much carbon remains, we can determine the age of the object. The half-life of carbon-14 is approximately 5,730 years old. So we're going to use that to answer these two questions here. It says, if we have 100 grams of carbon-14 today, how much would be left in 50 years? So in order to set up an equation, I need to know what the rate is. We know what the half-life is. That was given to us here. But we need to find the rate to plug it into our formula. So our half-life is 5,730, that was given to us, and that's equal to the natural log of 2 over r. So when we solve for r, we get the natural log of 2 divided by 5,730. When we put this into our formula, remember that this should be a negative number because this is a decay problem. So the problem tells us we start off with 100 grams. So that's our initial value that we put here. Here's our rate that we put in as a negative value, and here's our t. Wants to know how much is left in 50 years. So we're going to put in 50 years for our t and see what's left. When we do that, we get 99.40 grams. Okay, now let's look at the last part of this question. If an artifact that originally contained 100 grams of carbon now contains 10 grams of carbon, how old is it? We're going to round our answer to the nearest 100 years. So we're starting off with 100 grams. We end up with 10 grams, and we want to know how much time has passed, and that's how we figure out how old it is. So I'm going to put in 10 for our final amount. I'm going to put in 100 for our initial amount. Here's our rate that we found in the first part of the question. What we need to do is solve for t to tell us how old it is. So I'm going to divide both sides by 100. So I'm going to get 1 over 10 here is equal to e raised to the power of the rate times the t. I'm going to take the natural log of both sides. So that's going to give me the natural log of 1 over 10 is equal to negative natural log of 2 divided by 5,730, and that's all this rate is multiplied by t. So the last step is to divide by what's in front of the t on both sides, and I'm going to get that t is 19,035 years. So according to the question, if we round it to the nearest 100 years, we would put our final answer is that this object is about 19,000 years old.